Okay, am I speaking loud enough? Okay, so the topic I'm going to talk about today is called collaborative SNARK, and this is a paper from Dan Bonnet in 2021, and this is more from an engineering perspective rather than a mathematical perspective. So what's the problem it's trying to solve is that, sorry, I cannot breathe. So for SNARKs, there's a limitation that currently there's only one party can host the witness and then use that witness to generate proof. But in real world use case, there are a couple times that we need multiple parties to compute the proof together. So the conventional ZK SNARK is something like this. And collaborative SNARK is something like this. So basically, you can see this as you separate the witness into parts of them. And this is good because imagine if you are using a phone and you want to generate proof, the computation resource is limited. If you separate your witness to 3 other servers and ask them to help you to compute the proof, then you're not going to worry about single one server knows your secret and it's not a secret anymore. And currently there's a company that's doing this called Tesio, if you forget. Okay, and so a very naive way to think about this, making a SNARK into multi-party SNARK, is to use an MPC. And if we were to use a generic MPC to wrap over the proving stage of a SNARK, so to be more clear, for multi-party SNARK, the only thing that changed from here is only the proving stage. So before proving, we were only using one witness, and now we're making it into something like this. And generate proof. So the naive solution would be something like this, MPC, and then wrap over proving stage. But this is, it theoretically can work, but in practice, this will be super slow because proving itself is 1,000 times slower than the verification. And the MPC, generic MPC, is 1,000 times slower than the underlying operations. So what this paper proposed is actually a very smart, couple smart tricks that could combine MPC and ZK SNARKs together. So how it's done, I can cut it into 3 stages. MPC, SNARK, ZK SNARK, and then optimize. And in this stage, our goal is to find something that is SNARK friendly. So in this paper, they mentioned 2 different MPC schemes. One is called SPEEDS, and another is called GSZ. So SPEEDS and GSZ are both linear secret sharing schemes, and SPDZ is from addictive secret sharing. I'll just use SS. And GSZ is using Shamir secret sharing. The difference between these 2 is that SPDZ is dishonest majority. And GSZ is honest majority. And what does this mean is that in SPDZ, if one single party is not behaving correctly, SPDZ will know exactly what happened. And if GSZ, if one party is behaved dishonestly, the computed result, you will still get a computed result without knowing that it's actually broken. So how it's done is that SPDZ is including MAC during the computation process. So the input will be XI from different parties, and then MAC. So this MAC code is a message authentication code, yeah. So this will, so throughout, because this is additive, so we can just check the final sum of this MAC across different parties and make sure that all the parties are behaving correctly. And for for GSZ, there's no this functionality inside. So actually, when we are doing the coSNARK, we have to check for every multiplication tuple. Let me use XYZ. So for every computation in GSZ, we actually need to check this is correctly before we can move forward. So GSZ is actually, in normal computation, SPTZ is slower in the sense that it needs to compute 2 times, like X and also MAC. But GSZ is slower in the sense that we will need to verify XY equals to Z is computing correctly before we go forward. So there's actually an interesting evaluation in a later stage of this paper saying that if we see like the parties and slow down. At first, GSZ slowdown is actually slower, but then when the party grows, because we need to calculate this, and this is linear to like the computation included, so it's actually going like this. And for SPTZ, it's like started higher, but it's like growing slower. So this is SPTZ. And that is GSZ. Okay. And so for zk-SNARK, I'm going to focus on Planck implementation. So in Planck, I'm speaking steps. Okay, let me talk about polynomial commitment scheme in zk-SNARK first. So for the zk-SNARK step, our goal is to find something that is we can just distribute. We can just do it in the distribution. I'll just write this. So our goal is to find a distributed like polynomial commitment scheme. And in this paper, it's using KZG as an example. So before the conventional KZG, we have set up, commit, proof, and check. And in a distributed way, because the function fx is already shared between different parties, so the setup and check, we can just leave it at the same. But the question is, how do we generalize KZG so that the commitment and proof stage can be done like across different parties? And the answer is actually quite easy because the MPC scheme we're looking at, they are using linear combinations. So we can just use linear combinations for the commit and proof stage. So here we just do each party. I'll just use commit for example, but the proof is exactly the same. So I will use C for commit. Each party I will compute CI. And CI is essentially like the parts of the function that they know. So Fj I denotes as like the parts of the function that the party I knows. So the party just computes the commit to that part. And then we combine all the CIs together to get Z. And then the check part, the proof part is exactly the same. So we like compute the proof with the part that the parties know. And then we combine them all together to get a pi. So this is how it looks like from the polynomial commitment scheme part. So after that, we have a SNARK-friendly MPC. and we have a distributable polynomial commitment scheme. So now we need to optimize it. So using Plonk as an example, there are some gadgets that we use in Plonk, right? So we have FFT, we have MSM, we have polynomial division, we have, what else? Oh, we have product check, yes. So how do we do this in the MPC style is a problem. So we wanted to make it as efficient as possible. As it turns out, FFT and MSM itself, they are already linear operations. So it's actually, we can just, each party just computes the FFT of their part, MSM of their parts, and locally, and then we later combine them together. So it's actually not inducing any communication cost. And it's quite exciting because then these two parts, like the biggest bottlenecks, are not introducing more overhead in the MPC process. And now we look at polynomial division. So the polynomial division is in the process of KZG. And in the process of KZG, we actually divide it by a witness. So the polynomial we wanted to divide is independent from the witness, which means that we can pre-compute it and then just use it throughout the process. So this is also not a concern. Then we look at product check. So product check is something we're concerned in because we think that it might need sequential computations to get the result. And here, it's actually introducing a trick called, what is bar alien and beaver. It's introducing this trick to help us to distribute the computation for product checks. And how it's done is that first, Oh, okay. Well, time's up, but that's the best idea of this paper. So to combine MPC and check.
Is that bar in beaver, is that a garbled circuit?
No.
Oh.
I think not. If